So if you remember point slope, remember your equation y minus y sub 1 is equal to m times x minus x sub 1. So if you remember, it is okay to leave your equations alone in point slope form. What you're going to do is you're simply going to take this equation and you're going to solve it for y. So I'm going to add y sub 1 to both sides. Y is equal to m times x minus x sub 1 plus y sub 1. So just changing some notation here, this is my f of x, which is approximately equal to f of x sub 0 plus f prime of x sub 0 times x minus x sub 0. You're going to be given an x value to approximate. So what we're going to be doing is we're going to be plugging in that x sub 0 for whatever value they want me to approximate. This is what we call the local linear approximation, or tangent line approximation of f at x sub 0. Again, x sub 0 is some value that's going to be given to us. That's what we're going to be estimating. So when I have my L of x, this is equal to f of x sub 0 plus f prime of x sub 0 times x minus x sub 0. It also can be referred to the linearization of f at x sub 0. Because remember what we did was we started with that parabola x squared plus 1. We're zooming in and we're going to linearize it at that particular point, and we're using a tangent line to come up with an estimation. Now, there's two types of estimations that can occur when you're using linearization. One is an overestimation. So when we plug these values into the tangent line, we may come up with a value that is slightly larger than what the actual value is. And again, this is going to occur when the graph is concave down. So for example, let's suppose I have a graph that's concave down. So this is my f of x. And the point that I'm finding the equation of my tangent line, let's suppose, is right here. And I write the equation of my tangent line. And I'm going to call that L of x. So what's happening is when I pick this point, x sub 0, that's on the tangent, that's on the graph of f of x. What's happening, as you can see, the tangent line is going to be above f of x. So remember, I'm taking this x value and I'm plugging it into the tangent line. So you can see that the points on L of x are above or are going to be greater than the values on the function. So what happens is I know when it's concave down that my L of x has to be greater than f of x. The second case scenario is when you're going to have an underestimation. And an underestimation is going to occur when the graph is concave up. Because what happened is the linearization falls below the graph. So for example, I have my graph that's concave up. There's my f of x. Here is my tangent line. So you can see if I pick a point on f of x, that this is going to have to be an underestimation. Because if I pick an x value on f of x, notice the actual y value is going to be greater than the y value that is found by that tangent line equation. So your f of x is greater than L of x. And in chapter 4, we're going to talk about concavity a lot more, and the second derivative test checking for concave up and concave down. We'll be checking a lot more of that concavity. So any questions so far? So now let's take a look at an example. we want to find the local linear approximation of the cube root of x at x sub 0 is equal to 8, and we're going to use this to approximate the cube root of 8.1. Graph f and the tangent line together, and then we want to find the relationship between the exact and the approximation, and find out whether it's an over and under. First of all, anytime they're asking you to find local linear approximation, you're simply always going to start by writing the equation of the tangent line, which again we know in point slope form is going to be y minus y sub 1 is equal to m times x minus x sub 1. Remind me again what two things you always have to know to write the equation of a line. Point and a slope. So they're giving me an x value. The x sub 0 is 8. So I know I have 8 comma something. How do I find the y coordinate? When x is equal to 8, how do I find the y coordinate? Plug it in. Plug it in. So again, I plug it into my original because I'm finding a point on that particular function. So f of 8 is equal to the cube root of 8. And what's the cube root of 8? 2. My point is 8, 2. How do I find the slope? Slope comes from the what? Derivative. So I have to take, so f of x is, again, I'm going to change that cube root of x into x to the 1/3. So the slope is going to be, by using my power rule, 1/3 x to the what? Negative 2/3. Or 1/3 x to the 2/3. So that's not my slope, that's the derivative. So how do I calculate the slope at the point 8, 2? What am I going to have to do? Plug in the x value. So I know that f prime of 8 is going to be equal to 1/3 times 8 to the 2/3. Oh my gosh, I remember how to evaluate a fractional exponent. What is 8 to the 2/3? 4, and then 4 times 3 is 12. So then my tangent line at the point 8, 2 is going to be y minus 2 is equal to 1/12 times x minus 8. So far, this shouldn't be anything new than what you either did last year, whether it was in pre-calc honors or AB, writing equations of tangent lines. So now to find my local linear approximation, all I'm going to do is take this equation and solve for y. So how do I solve for y? What am I going to do to both sides? I'm simply going to add 2. So y is equal to 1/12 times x minus 8 plus 2. So then my linearization, I can call this my L of x, is equal to 1/12 times x minus 8 plus 2. So now I can use this line to estimate what the cube root of 8 plus 1 is going to be. So to figure out what f of 8.1 is approximately equal to, all I'm going to do is take out the x from this equation, and I'm going to plug in an 8.1. So I've got 1/12 times 8.1 minus 8 plus 2. When I subtract 8.1 minus 8, that's going to give me what? 0.1, or as a fraction, it's going to be what? 1/10. Remember, fractions are a heck of a lot easier to work with than decimals. Remember, 0.1 is equivalent to 1/10. So I end up with 1/120 plus 2, or about equal to 2, and 1/120 as a mixed number. And this is about equal to 2.05 if you change that into a decimal. All right, so any questions on that?
Why do you use
So what you're doing, your original function is cube root of x. So again, 8.1 is the x value you're using to approximate. Because without a calculator, we don't really know what the value of the cube root of 8.1 would be. So, good thing these things are adorable. So just to show you how close that this approximation is going to be, if I type in the cube root of 8.1, notice I end up with 2.008. So notice how close, without even having to use a calculator, how close we can get an approximation of the cube root of 8.1. All right, so any questions on that local linear approximation? So again, it's just basically taking your tangent line, solving for y, and then plugging in the x value that you're trying to approximate. All right, you guys go ahead and try the next one. So hopefully we at least got the tangent line down to this particular part when we solve for y. Are we good on where I've got that so far? And then when I plugged in 0.99, I end up with an approximation of about -1 and 3 over 100, or -1.03 as a decimal. All right, any questions on finding the approximation of 0.99? So question is, how close is it? Well, the actual value, if you actually plugged in 0.99 into the original function, you can see how close our approximation was of -1.029. So you can see how well of an approximation we're coming up with. All right, so, but now without a calculator, the question is, are these over or are they under approximations? Let's take a look and let's go back to example 1a. Remember, example 1a, I ended up with an approximation for 8.1 of 2.05. Let's go ahead and let's graph f of x. So the graph of f of x, remember, it's your cube root function, the cube root of x, which I always call this graph, always looks like that slithering graph to me. I don't know, it always looks like a snake or something. There's f of x. And I know that when x is equal to 8, the y value is 2. So 8.1 is going to be right about here. So there's my tangent line. So without even plugging in the exact value into my calculator, it appears that this is going to be what? An over or under approximation. What do you think is happening? Over approximation. All right, again, when we get into chapter 4, some of the graphs, it's hard, especially cube root of x, because it increases at a very slow rate. We'll be able to get that second derivative test to confirm whether it's an over or under approximation. But now if you take a look down here, so this is going to be an over approximation. So when we take a look at b, 2x to the third minus 3x. Again, if I factor out an x, that's going to give me a 2x squared minus 3. So I know I'm going to have an x-intercept at the origin. Again, and it's a polynomial function. Remember, your end behavior of polynomial functions, odd degree, leading coefficient is 1. I know I'll have another x-intercept at the square root of 3 over 2. Again, just a sketch. And it's going to have to come back up somewhere. So I know I have the point, oh, I did a terrible graph. Should be 1, -1. So this is probably over here. Because I have the point 1, -1, so I should have come back down much quicker. It was a rough sketch. So at 0.99, this is a little bit easier to tell what's happening with this particular curve. Is it concave up or is it concave down? The graph of f of x. What's happening here at 0.99? Is it concave up or concave down? Concave up. Remember, up like a cup. So if it's concave up, is this going to be an over or under approximation? Under. You can see how the tangent line is below the graph. So therefore, I know that this is going to be an under approximation. Because remember, we got negative 1.03 versus that negative 1.029 that I showed you what the actual values are. Remember, because they're negative numbers, negative 1.03 is less than negative 1.029. So any questions on local linear approximation? That's pretty much it to local linear approximation. That's why I said we're going to do L'Hopital's rule as well as, so as you came from pre-calc honors, I'm sure your classmates have probably filled you in on the nice shortcuts to doing some of these limits. I always remember L'Hopital's rule begins with an L. Limits begin with an L. So this is a limit rule. This is a shortcut to doing some limits. So suppose you're trying to find the limit of a fraction, and again, you have to have a ratio. And suppose when you do the limits, you get 0 over 0 or infinity over infinity. L'Hopital's rule only works is after you try direct substitution and you get 0 over 0 and infinity over infinity. And you must show that you get the 0 over 0 or infinity over infinity and you're moving to L'Hopital's rule. You've got to show that. This is the one and only time you are allowed to take the derivative of a numerator and divide it by the derivative of the denominator. You're not finding a derivative, you are finding a limit. So remember, when we do get 0 over 0 or infinity, this is called your indeterminate form. So L'Hopital will convert your indeterminate form into a limit involving derivatives that make it easier to evaluate. So as long as you get 0 over 0 or infinity over infinity, to calculate this limit, you can find the limit as x approaches a by taking the derivative of the numerator and dividing it by the derivative of the denominator. Then try direct substitution again. You can do L'Hopital's rule more than once. Let's suppose you take the derivative of the numerator and derivative of the denominator. You do your direct substitution and you get 0 over 0, infinity over infinity. Again, as long as you get that indeterminate form, you can take the derivative as many times as necessary until you can find it. All right, so again, you can also apply if you get infinity over 0 or 0 over infinity. So let's take a look at this first one. You must show the indeterminate form before you take the derivative of the numerator and derivative of the denominator. So we always try and find limits, remember, by direct substitution. So when I plug 0 in for x, well, what's the sign? We know 5 times 0 is 0. What's the sign of 0? 0. What happens in the denominator? 0. So now what I can do is I can move on to L'Hopital's rule. And it's okay to abbreviate L'Hopital's LHOP. You've got to state this. You've got to write this. Free response, they are very picky about notation and justifications. You've got to show a 0 over 0 and that you're going to apply L'Hopital's rule. So now I'm going to go ahead and I'm going to take the derivative of the numerator and derivative of the denominator. Again, you're not finding derivatives, you're finding a limit. This is the one and only time you wouldn't have to use quotient rule. Because anytime you know to find the derivative of quotient, you've got to use that quotient rule. What rule do you have to use to find the derivative of sine 5x? It's a what? Your favorite. Chain rule. Because the outer function is sine, the inner function is 5x. What's the derivative of sine? Cosine. So I have the cosine of 5x times what? 5. Over. Do I have to use the chain rule in sine of 3x? Yes. And again, derivative of sine is a cosine times the derivative of the inner function, which is 3. So now try my direct substitution again. So plug in your 0. So I end up with a cosine of 0 times 5 over the cosine of 0 times 3. And what's the cosine of 0? 1. So I know that I end up with this limit to be what? 5 over 3. So any questions on A and how L'Hopital's rule works? What happens if you try and do direct substitution on part B? What happens if you try and do direct substitution? 0 over 0. So then you can go ahead. You guys go ahead and try and find the derivative of the numerator and derivative of the denominator. You guys do that one. Any questions on that one? Let's take a look at C. How the heck do I plug in infinity in here? When you remember from limits, anytime you're asked to take the limit as you're going to infinity, what you're doing is you're looking at end behavior. And if you remember, the end behavior is dictated by asymptotes. So let's take a look at natural log of x. What is the end behavior of the natural log of x? We know there's a vertical asymptote. Do you remember for natural log of x where the vertical asymptote is? Where's the vertical asymptote? Do you remember for natural log of x? Can you take the natural log of 0? No. So you have vertical asymptote here. Remember, your natural log functions look something like this. So as x is going to infinity, what's happening with the behavior of the natural log of x? Is it approaching a number? Is it approaching positive infinity? Or is it approaching negative infinity? Positive infinity. So then when I ask you the question, what's the limit as x goes to infinity of the natural log of x, that numerator is just going to be infinity. In the denominator, you have the function y equals x, which is just a line going through the origin. So my question to you is this. What's the end behavior of y equals x? Infinity. So notice when I take the limit as x goes to infinity of natural log of x over x, I get the indeterminate form of infinity over infinity. So I can go ahead and I can apply L'Hopital's rule. So you guys go ahead and finish that limit for me. One divided by a really large number. Getting really close to 0. Exactly. You need to remember that. Anytime you're taking 1 and you're dividing it by a very large number, it's going to be equal to 0. 1 divided by a million, you're getting really close to 0. Okay? So any questions on that? You guys go ahead and try D for me. All right, a couple other things about L'Hopital's rule. Like I mentioned a few minutes ago, if you get the determinate form, again, after doing direct substitution, you can apply L'Hopital's rule again. You can apply it as many times as needed as long as you're getting that 0 over 0 infinity over infinity. All right, so for example, let's take a look at A. You guys probably don't even need to use L'Hopital's rule for 2A. Because when we talk about the limit as x goes to infinity, you are looking at the end behavior, correct? And this is a rational function, and what is that rational function going to have? It's going to have an asymptote. It's going to have a horizontal asymptote. Where's that horizontal asymptote going to be? Remember when you did limits and you go to infinity, it's just a horizontal asymptote, correct? Which is going to be what? 5 over 7. And I agree 100% with that. Remember, if the degree of the numerator is the same as the degree of the denominator, you make a ratio of the leading coefficients to find the horizontal asymptote. If you forgot, now that you know L'Hopital's rule, you can certainly use L'Hopital's rule, because when we do direct substitution, you're going to get infinity over infinity. So the limit as x goes to infinity. So you can take the derivative of the numerator, which is going to give me a 15x squared minus 8x. Again, derivative of 1 is going to go to 0, over 21x squared plus 2x, or just plus 2. When you try and do direct substitution again, you're going to end up with infinity over infinity, because you get a really large number on the top and a really large number on the bottom. So you can apply L'Hopital's rule again. So the limit as x goes to infinity of 30x minus 8 over 42x. So where does that 5 over 7 come from? I still have infinity over infinity. So when I do my L'Hopital's rule again, that's going to give me 30 over 42. And what does 30 over 42 reduce to? 5 over 7. So again, if you ever forget those asymptote rules, you can always try using L'Hopital's rule. Okay? What about B? Let's talk about B for a minute. Do I really have to do L'Hopital's rule 50 times? What eventually, if I did L'Hopital's rule over and over and over again, what eventually is going to happen in this numerator? I'm eventually going to end up with a what? Going to end up with what? Yeah, Christian?
An extremely large number.
Times what? 0. Because I'm going to take the derivative of 50x to the 49th, then it's going to become something x to the 48, something x to the 47, x to the 46, x to the 45, etc. All the way down to an x to the first, correct? And then what happens when I take the derivative of x to the first? Yes, I have a really, really, really large coefficient. I have a really, 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 really large number here. Times x to the first. And then when I take the derivative of this x to the first, it's going to be that really, really large number times what? 1. And then I'm going to take this really, 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 really large number times 1 and take the derivative of this, and this derivative is going to go to what? 0. 0 divided by a really, really, really large number is still going to be what? 0. 0. So eventually this is going to go to 0. Because again, remember, the limit as x goes to infinity. I know this is going to be infinity over infinity. It's going to be 50 times x to the 49th all over 2e to the 2x. But what eventually is going to happen here, it's going to become 50 times 49 factorial times 0 over a really large number. So it's going to go to 0. That's 50 times 49 times 48 times 47 times 46 times 45, etc. Remember, that's a factorial. Remember, in order to use L'Hopital's, you've got to make sure you have a quotient. So you may have to do some rewriting first before you can actually apply L'Hopital's rule. So for example, let's take a look at the limit as x goes to infinity. Right now, you agree with me that this is not a quotient. Anybody see anything on how I can make this a quotient?
Negative exponent.
Get rid of the negative exponent, exactly. So I can write this as the limit as x goes to infinity of x over e to the 2x. When I plug in infinity, I know this is going to be infinity over infinity. Because remember, in case you forgot, the end behavior of e to the 2x is approaching positive infinity. That 2x is just a horizontal stretch or compression, so it's not affecting end behavior, that 2x exponent. So now when I go ahead and try and find the limit as x goes to infinity, that's going to be 1 over 2e to the 2x. And we just talked about this a few minutes ago. X is a really, 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 really large number. So 1 divided by e raised to a really, 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 really large number is going to give me what on the bottom? It's going to give me a really, really, really what? Large number. So remember, 1 divided by a really, really, really large number is getting really close to what? 0. Let's take a look at the last one, B. Oh boy, how am I going to write this one? Trig functions are the easiest ones, if you can, to write as quotients. because you have all those reciprocal identities from trig. Can you remember what the tangent of x is equal to? You have a reciprocal identity. I agree it's sine over cosine, but let's not bring more than one trig function into this problem. So we what? Yeah, Christian? 1 over cotangent of x. I'm not saying you couldn't get there if it's sine over cosine, but it may be easier to have it so that you only have one trig function in there. So what I could rewrite this as is the limit as x goes to 0 from the right of natural log of x divided by the cotangent of x. So I did the graph of natural log of x a few minutes ago. What's happening with the limit as x is approaching 0 from the right? It's going towards what? What's the behavior? It's going towards what? Negative infinity. Oh, now you gotta remember the graph of cotangent of x. Where does cotangent of x have asymptotes? I love all this trig. What? I have to remember all my trig? You have vertical asymptotes of cotangent. Well, we know tangent's undefined where? Tangent's undefined at negative pi over 2 and pi over 2, right? That's where tangent. So now, where is cotangent going to be undefined? It's going to be undefined at 0 and pi. So now tell me, what's happening with the behavior of cotangent of x as x is approaching 0 from the right? It's going towards what? Infinity. Infinity over infinity or negative infinity over infinity, it's still an indeterminate form. So then I can use L'Hopital's rule. So the limit as x approaches 0 from the right, the derivative of natural log of x is going to be 1 over x. Over, what's the derivative of cotangent of x? Negative cosecant squared x. You certainly will want to clean this up as much as you can. Is there a way that I could rewrite negative cosecant squared of x so that's not a fraction? What is negative cosecant squared x equivalent to? Negative 1 over sine squared x by reciprocal identities? Yes? Remember the reciprocal of cosecant is sine? So I can rewrite this as the limit as x goes to 0 of 1 over x divided by negative 1 over sine squared x. Any questions on what I've done so far? So I know when I divide by fractions, it's equivalent to multiplying by the reciprocal, correct? So I know that I can multiply this by 1 over x times negative sine squared x all over 1. So the limit as x approaches 0 from the right is negative sine squared x all over x. Shoo, I hope I'm done. Am I? No. Because what's my limit going to be by direct substitution at this point? 0 over 0. So guess what I can do again? I can do what? L'Hopital again. So you guys go ahead and finish that for me. Find that limit. So when you have those trig functions, problems are pretty obvious because they're really ugly limits usually. Usually you can almost recognize, but you've got to show if it's a free response and you don't show that 0 over 0 and you actually write L'Hopital and it's okay to abbreviate, they won't give you credit. A lot of the justifications on the free response questions, they're very picky about that. You just cannot jump to L'Hopital's rule without showing that 0 over 0 or infinity over infinity and write LHOP or L'Hopital's rule. All right, to justify why you're taking the derivative of the numerator and derivative of the denominator. That's the rule you're applying. All right, any questions on L'Hopital's rule or that local linear approximation? All right, then let's talk about what's next class. So we talked about how test is coming up next week. So everything on chapter 3